Hey, what's up, guys? This is Chung here. So this time, today's daily challenge problem, right? Number 45, jump game number 2. So you're given like an array, right? And you're initially standing at first index, and each element in this array represents the maximum jump length from this position. And your goal is to reach the last index in the minimum jump. And you can assume that you can always reach the last index. Okay, pretty straightforward, right? Basically, you have a numbers here. You have a list of numbers here, and at the beginning, you are standing at this one, and your goal is to jump to the end, to here, right? So from index 0, you can jump 2, which means that from here you can jump to here, right? That's the basically that's the maximum jump length, right? Which means that the furthest you can jump is this one, but you can also jump to 3, right? That's why, for in example 2 here, the answer is 2. Basically, from the optimal solution is from 2, we can jump from this first index, we can either jump to 3 or 1, but in this case, we jump to 3. And then from here, we can jump all the way back to the end. That's why the answer is 2, right? Yeah, so that's it, right? I mean, so for this one, it's obviously we can I think we can use like a DFS approach. I mean, basically, but probably we cannot just blindly use like brute force way, because let's say for at each of the location, when I'm saying brute force, I mean from each of the location, we simply just try to jump to each of the places, right, of this like kind of array. But probably we can also do that, because even though this kind of numbers, it's pretty big, but the length is only 1000, right? So which means that at each of the location, the maximum iteration we need to do is only 1000, right? That's why even with a brute force, we can probably still solve this problem. But if this one is like also 10 to the power of 5, right, the length of that, no, then probably will not be able to use the brute force way to solve this one. Basically, when I say brute force, I mean at each of the location, I try each of the possible jumps, and then I also maintain like the steps we have taken, right? And then in the end, we just get the minimum out among all of those kind of possible ways. Okay. So instead, for this problem, we can use like a greedy, right? Because it's kind of obvious that we always want to jump as far as possible, right? And so for this one, actually, it's another very classic example of this kind of called lazy greedy. For those who don't know what lazy greedy is, so lazy greedy is something like we simply just keep going, and whenever we cannot moving forward, we go back to see what was the what could have what we could have done optimally to make us going further, right? So in this case, is that let's say we at the beginning, we're standing at here, we whenever we cannot moving forward, we go back to see, okay, so when was so what was the maximum place we can jump to uh, from the indexes we have been processed so far. If right, if that, and then we pick the biggest number from one of them, right? And then it means that okay, so since we cannot moving forward, it means that we will basically going back to that index that can make us jump the furthest, and then we'll jump from there. So which means that we have 2, 3, 1, 1, 4, right? So our initial state, since we are standing at index 1, 0 here, from here that we don't have any other options, but we can only jump to here, right? Which means that the furthest we can jump is 0, 1, 2. Okay, right? That's the furthest we can jump. And then from here we come to here, right? So from here, we see that okay, so the current index is 1. 1 is still within 2, which means that we don't need to jump, right? But we can maintain like the maximum places we can reach, right? So in this case, what will that be? Basically, it will be 1 plus 3 equals to 4, right? If we ever want to jump from here. And then from 1 here, 2 is still not greater than 2 here, which means that so here we don't need to jump either. So here what will be the maximum place we can jump to from here? It's going to be 2 plus 1, right? Which will be 3, right? 3 is smaller than 4, so that's why we're still keeping this 4. But when we reach here, the I is 3, right? 3 is greater than 2. So which means that if we ever want to reach to this place, okay, we have to make one jump, right? But which jump? Of course, we want to make jump from this one, which is the biggest one of this one. And whenever we make a jump from here, then we know that okay, the farthest we can go is 4, right? So which is this one, that's why when we reach this 4 here, we know okay, we still don't need to make another jump. Okay, that's basically the idea of this kind of lazy greedy approach. So let me try to implement the first brute force solution real quick, just to show you guys what did I mean. Okay, so it means that we're gonna have like a dp function here, so the only state we have is the index. Basically, dpi index means that from this current place, right? What's the minimum steps we need to make to reach to the last index, right? So that's gonna be the dp solution for the first brute force way, And so it's pretty straightforward. So at the beginning we have system.max, right, size, and then for I, basically we from the current index we try to jump to each of the possible places, right? As long as we can reach that, right? Basically, it's going to be a index plus 1, since we want to jump at least 1, right? And then we stop at index plus the nums dot index and then plus 1, right? And then we have answer equals to minimum of the num answer dot 1 plus because we make one jump, right? The dp of I, right? And then we return the answer, right? So what's going to be the exit condition where the if the index basically is either equal or greater than n minus 1, right? And then we simply return 0. We also use this kind of greater. It means that since this range could be more a bit exceeding the length of this index, the length of the nums here. If that's the case, we also return 0 because we know okay we can also jump to the last one, right? So yeah, and then we simply return the dp0, right? That's it. So if I run the code here, oh, okay, I forgot to define this length here. So it's gonna be the length of nums. Okay, cool. So if I submit, right, there you go, right? So it works. Now, as you guys can see, so for this one, the time complexity for this, since here we have n, right? And for each of the n here, we also gonna do another for loop here. So assuming this kind of have the same magnitude, so it's gonna be an n squared time complexity, right? That's why I said, this one can pass here because the length is pretty small. If this one is 10 to the power of 5, this solution will TLE. Okay, cool. So, and then for the greedy one, right? And then, which means we need a better solution for this one, which is a greedy one. In this case, it's like a lazy greedy, right? So for the lazy greedy, we also need kind of the length of nums here, and so the answer we start from 1, right? We start from 1 on. No, actually, there is a special case, because here, we're assuming we'll make at least one jump, but this length, could be equal to 1, right? So if there's only one like numbers, it means that we can simply return 0 because we don't need to jump. So basically, if the n is equal to 1, right, we return 0, right? Otherwise, we're assuming we'll at least make one jump, right? And then the max we can jump is at the starting point is nums of 0, right? And then we have a current. Basically, the current will also be a nums of 0. So this current means that the so this one is the current farthest place index we can be. Okay. So that's why for I in the range of 1 to n, right? We compare if the I is greater than the current, right? So it means that if the current I has has passed the farthest index we can be, right? And then it means that we have to go back to find, basically we need to jump, right? But which one we need to jump to? It means that we'll jump to the place where this like the maximum can tells us. That's why first we're gonna increase the answer by 1, right? And then we're gonna jump to that place. If we jump to that place, we're gonna update this one. Current is gonna be the maximum, right? And then the right thing is that we're gonna keep maintaining this max, right? And then we have this kind of I plus nums I, right? And then we return the answer in the end. So I think that's it, right? Yeah, there you go, right? So as you guys can see, so this is how the lazy greedy works. Basically, the greedy means that we always maintain the maximum place we can jump to, for the index we have been seeing so far, and we never, and we just keep going, until we cannot keep moving. That's when we will go back to pick like a previously visited index position to make a jump, right? But which one we need to make? We always pick the maximum one, So for this kind of lazy one, for other problems, to use lazy greedy, we often use like priority queue, right? To maintain either the minimum or the greatest or the biggest, element. But for this, because for that one, because we might need to the reason we use the priority queue was because we might need to use some other like uh, element other than once we have used the biggest one. But for this one, we don't need to use a priority queue because um, we always want to basically use the since this thing is always increasing, right? That's why we always need to maintain like one maximum locations we could have ever jumped to, right? That's why whenever we cannot jump anymore, we increase the answer by 1, and then we'll update this current one, which means that okay, so now I'll make the jump, right? But I'll jump to the farthest place possible, right? And then the next, and then later on, when we then we can keep moving, right? Keep moving forward at least to this current place. Okay, and yeah. Yeah, and as you guys can see, this one is simply like a O of n time complexity, right? So even with like 10 to the power of 5, we can still pass. Yep, I think that's it, right, for this problem. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye-bye.